First, I would like to start by thanking the NSLondon for this opportunity, and it's been great meeting you all and hosting you guys. So my name is Bret, and I'm one of the early members in the iOS engineering team. Today, I'm going to share how we serve 27 million monthly active users with local first architecture. Before we dive into that, let me introduce you to Goodnotes once again. I will be quick. So Goodnotes turns your iPad into a digital paper, and it helps you take notes, annotate PDFs, and study them. Together with Apple Pencil, is as natural as pen and paper, but with all the benefits of being digital. For example, you can search your handwritten notes, correct them with spell checker, and solve handwritten math equations even, right? So Goodnotes is loved by students and professionals and other users all over the world. In 2022, we won the iPad App of the Year. And last year, we saw 27 million monthly active users. 3.7 million of them are teachers. And in just 1 year, they created 5.5 billion notebooks together. So this brings us to the topic of the day, right? How do we serve this many users or at this scale? As you can tell from the name of the talk, we achieved that by going local first. But what is local first? Local first is a set of principles and values to build software. But it generally refers to apps that store data primarily on the local device. They sync data with one or more backends in background, but without relying on them to function. So here are the 7 ideals defined in the original Local First manifesto written by our friends at Ink and Switch, which I highly recommend reading. So Local First is an ongoing movement, and it focuses a lot on end user benefits. Its ultimate vision is not easily achievable as of today. Still, by designing softwares with these ideals in mind, we believe that not only that will benefit end users, but it also helps developers and businesses to grow. Incidentally, the manifesto was published in early 2019, shortly after we launched Goodnotes 5, which was the version completely redesigned from ground up with similar principles and technologies in mind. So it's not difficult to find apps on App Store that are in line with these local first ideals. They store data on the local device, they work offline, many of them support sync and collaboration. These features are now considered standard by our users nowadays. In fact, we saw that firsthand when we launched Goodnotes for other platforms as a cloud-first app. The top feature request we get was offline support. We still get that request nowadays. But we have loads of this app. Not many of them are scalable. Part of the reason is that many started out as a single user or device app. It could be like a note-taking app, like a to-do list app. And for them, sync and collaboration were only added later on as an afterthought. We were once in a similar situation. So Goodnotes 4 was a UI document or document-based app that supports sync via iCloud Drive. It doesn't support or it doesn't give us much control over how data is synced or how conflicts are resolved. So when multiple devices edit the same document, we had to ask our user which versions they want to keep. This was a huge blocker to provide seamless collaboration experience for our users, not to mention real-time collaboration. This problem is not unique to iCloud Drive though. Most of these backend as a service solutions like Firestore, RAM, They provide their own conflict resolution mechanisms, which might or might not work for your app. Some simply doesn't support collaboration. Here, developers are at the mercy of the features provided by these vendors. So this is why when we developed or we designed Goodnotes 5, we invested a lot in distributed system technologies and design pattern that would give us full control over sync and collaboration. We had to rethink the architecture all the way down to data structure level. And the result is a backend and network agnostic model that continues to adapt to the growth of our product and business. And here's how. So Goodnotes 5 and 6 use CloudKeep as the primary sync backend, where data is stored in our users' private database. So data is actually attributed to their personal iCloud storage quota. So this accounts for the majority of our 5.5 billion notebooks created in 2024, meaning we don't have to go bankrupt to serve these users at scale. In return, we can be more generous with our freemium offerings. Even though CloudKeep provides data sharing APIs, we don't want collaboration to be locked in to one single platform, where a user must have an Apple ID to collaborate. So when a notebook is shared, an extra copy is synchronized with our own Goodnotes Cloud, allowing users from other platforms to access and collaborate. We also launched Goodnotes for Android, Microsoft, and Samsung tablets about a year ago in order to allow these users to access their libraries across platforms. We started rolling out using Goodnotes Cloud as the primary sync backend on iOS as well. Now, to provide a good real-time collaboration experience, especially in places where network is unstable, like schools, we support peer-to-peer sync between users via WebRTC. These sync operations with different backends and networks can happen simultaneously without any conflicts, thanks to the new data structure and architecture, which I will be sharing in a bit. But we don't have to stop there. In theory, we can support any cloud backend or communication channel for synchronization, be it like Dropbox, Bluetooth, or even like on-premise solutions. So Dr. Martin Kleppmann, who is like a pioneer of this local first movement, shared his vision of what the end game looks like at the local first conference last year. So end users can sync their data with interchangeable services so that they don't need to worry about companies going out of business. So that would require a standardized sync protocol that cloud vendors can implement. And we are likely years away from seeing that in reality. But what we have shared just now, at least on the client side, is not too far off. And we are instead taking advantage of this interoperability to scale our product and business. Now, let's discuss the technologies behind local first architecture. First, it is important to understand local first is a distributed system problem. When multiple devices go offline for an extended period of time and continue to modify the same content, there is no single source of truth. What you have instead are distributed states. So each device, which can belong to the same or a different user, has a copy or a replica. So each one is as true and as correct as the others. So you can treat each device as a node in a distributed network. All nodes will converge to a consistent state eventually when they have a chance to connect and sync data with each other, and when there are like no more updates. That's why we call it like eventual consistency. But one big challenge in distributed system is conflict resolution. Even more so for like mobile applications, where each node is a user device. And we cannot simply swarm and like run operations on demand. We need a way to resolve conflicts automatically. And that's where conflict-free replicated data types, or CRDT, comes in. So CRDT is a data structure that is replicated across multiple nodes or devices in a distributed network. It is a data type and algorithm at the same time that guarantees to resolve conflicts automatically and eventually. There are like many different types of CRDTs. Some are like simpler, like a row-only counter. Some are like more structured, like maps or like auto-merge, which promise better developer experience and ability to handle more complex use cases. But today, we will focus on one of them, last right win, or what we call LWW, and how we use it at Goodnotes. So LWW timestamp is a building block of our data model. We have a bunch of them, for example, like LWW string, LWW double, LWW page rotation, which I will be using as an example to describe how things work. So they all contain a LWW timestamp with a counter and a random value. So whenever we update a LWW data type, the known counter will be incremented by 1 locally. At the same time, a new value will be generated and assigned to random, which will be used to break ties when counters are the same between updates from different replicas. It is important to note that in a distributed system, we cannot trust the wall clock timestamp or like the device clock, as it can be ahead or behind or simply out of sync. Instead, we need to use the counter value as a logical timestamp to keep track of all these edits and updates. So we use these building blocks in our data model so that they support multiplayer from the ground up. So any property that is mutable by the user is wrapped by this LWW value. Here's a simplified representation of a page in Goodnotes. We allow multiple devices to update the rotation of a page, whether they are offline or like collaborating with other users. Each device keeps track of the LWW timestamp locally. So when they sync, we will simply merge the LWW values by picking the one with a greater timestamp. Here's an example of like a happy path, right? So we start with device A rotating a page by 90 degrees. So the LWW timestamp of the rotation of the page is at 1. So this update is synced to device B, and now both devices are at 1. When device B rotates the page again, or later on, we will increment the known timestamp by 1, so it's 2 now. So this update will then be synced back to device A, and everybody's timestamp is now 2. So this is the happy path, where like you work on one device, you allow data to sync to others, and you do the updates in order, right? But if both devices go offline and rotate the page without seeing updates from others, we have a conflict. And with LWW timestamp, we simply pick the largest timestamp. So here, in this example, we'll pick the rotation from B. Here, the counter values are the same. So we have to use the random to break tie. So device B's random is 3, it wins. You might ask, like, what if the random values are the same as well? So we have to then deterministically resolve it. There are like many different strategies. One is using the value itself. For example, we can always choose the smallest degree of rotation, or we always like choose true over false if it's a Boolean. The important thing is the result being consistent and deterministic, regardless of orders of update. So we have this resolved. So using LWW timestamp as like a building blocks also give us full control over the granularity of conflict resolution. So in the previous example, we only merge the rotation of the page without affecting other properties. But we can also use the timestamp as a version and merge or replace the entity entirely. This not only keeps our merge logic simple and fast, it also protects data integrity. So here is an example. So consider you have like an image, right, with two properties. Oh, by the way, we really have this data, like, yeah, it's from our app. So one property is the bounding box. The other is the actual rack with like a rotation. So the two properties are updated as a unit, right? So if we were to wrap them with two different LWW timestamps, one for the rack, the other for the actual rack, conflicts could be resolved separately, which might result in unexpected behavior. So here, if we use LWW as the version, we ensure the entire update is consistent. Another important concept is tombstone, especially in a distributed system, which is used to mark an entity as deleted. When the tombstone marker is synced to other devices, it triggers local deletion of the entity. So this results in a remove wins strategy where an entity is always deleted regardless of the updates made by other. And now on top of CRDTs, another design pattern we follow to achieve sync and collaboration at scale is event sourcing. I want to start by saying that event sourcing is not necessary to build local-first software. It adds complexities to the system, and we will cover that in a bit as well. But going back in Goodnotes, every user action results in an event, which is appended to an event log, and then locally we will project these events into states to be presented to our users and for other purposes. For example, when a user renames a document renamed event is generated, and then we have some projection logic, and in the logic we will merge the name property here, which is a LWW string, and we'll merge that with the current state of the document. So we see events as like global source of truth. So during sync, we exchange events instead of states with the backend. The device is responsible for projecting events from the backend the same way it does for events as a result of user actions, as we just saw. And seeing an event laterally describes the delta of a change to the state. We can easily achieve real-time sync by exchanging only unseen events between client and the backend, or directly between peers. Now, since we allow devices to make concurrent edits offline, it is possible to have different order of events between them. We allow such a discrepancy as long as the causal order is in place. By causal order, I mean in this example, document created event must precede any other events for updating the same document. Otherwise, we would not have any document state to merge events with, because the state has to be created by the document created event, right? So as previously mentioned, event sourcing comes with some trade-offs and challenges, right? In addition to state, you also need to keep events around as they are the source of truth, and you need to be ready to sync them. Now imagine you move a document 1,000 times. So if you sync the entire event history to a new device, all events will be projected and you will see the history replay in front of you. Meaning you will be seeing the document moving here, there, but we are only interested in the latest state. So we solve this problem by what we call baselining. It is a process where we reduce the entire history into a subset that are enough to recreate the current known state of an entity. And we do it during sync. That also improves like the traffic and storage. So finally, there are like events from external systems that we need to translate into our own so that we can project states together with our events in our own domain. For example, when participants and permissions are updated on CloudKit, let's say we are doing like a sharing, document sharing, we need to update certain properties in the document state. So to achieve that, we have to generate what we call like a local event to kind of represent the updates happen on CloudKit so that we can project with our projection logic in the same way, right? But these events, why we call them local, they cannot be synced outside of our domain because it comes from CloudKit, which is like a centralized server. And what we're dealing with is, again, a distributed system. So in conclusion, we looked at the promising local first movement in architecture, how it helps scale our product and business. We also dive into how CRDTs and event sourcing give us full control over sync and collaboration, which is the key to a scalable local first software, at least from our point of view. Now, whether you're new or like an expert to this topic, feel free to ask any questions or grab me for a chat. Also, we have some openings, so remember to check out our openings here with this QR code. So that's everything to present. Thank you.